Hello, everyone. Welcome to discussion hour today. Today we will be hearing part of one chapter of his dissertation by Peter Miller. So Peter studies mechanisms for dewatering in the upper portions of subduction zones through laboratory experiments on cores collected from drilling expeditions. He focuses primarily on the Eastern Aleutian and the northern Hikurangi margins where fluids help modulate and control a spectrum of slip behavior. Take it away, Peter.
Great. Well, thanks for coming, everybody. Kind of give myself a better. That's basically how I was going to introduce this chapter anyway. Basically, the idea behind this project that I've been working on as part of my second chapter of my dissertation is looking at consolidation behavior in sediments as they're being under thrust in the upper portions of accretionary margins. Specifically here, looking at the Eastern Aleutians, but this sort of workflow can also be carried over to other places around the world that have under thrusting sediments to depths of about 10 kilometers. So looking at how those sediments dewater mechanically, and then how that pressure is either built as pore pressure or comes out and basically reducing the hydrostatic conditions, if that's the case. So, and how that helps with controlling slip and slip behavior on the fault zone. So a little bit about me. First, I did my undergraduate at Bates College in Maine. So I come from a structural mapping background, looking at Paleozoic metamorphic rocks. Then I did my master's at Penn State, where I looked mostly at how permeability is reduced by deformation bands in sandstones. Then moving on to my PhD here, where I'm looking at mechanical properties of subducting sediment and how that sediment dewaters as you compress it beneath the decollement in the upper portions of the subduction zone. One of my favorite experiences here was a field season where I spent out on a ship where we did magnetotelluric data profiles, collecting magnetotelluric data along the Eastern Aleutian. So this is across the Eastern Aleutian margin. Now this project is sort of tangentially related to what I'm working on here, because magnetotelluric data by its nature is typically looking more at deeper fluids. So much greater depths, hydration state to much greater depths than what I'll be talking about here. But in terms of the context of fluids and subduction zones, it was a really cool experience and something that it would be awesome to get on again. But yeah, so that was just me on the ship. So the motivation for this project, and most projects looking at seismic hazard and subduction zones, is that they are a significant hazard to populated regions around the world. We have different very great earthquakes that have occurred in near populated regions like Sumatra in 2004 and Tokuoki in 2011. We tend to not see destructive seismic behavior everywhere, because slip, as we've sort of observed over the last 20 to 30 years, sort of follows a spectrum of behaviors, ranging from basically slow slip, which is energy release over the course of the time scale of weeks to months. So this could be a magnitude 8 over the course of 2 months, to low frequency events termed tremor, very low frequency earthquakes, which are seismic, but they're very low frequency, all the way down to seismic events like our great earthquakes that we see at these margins. The stability of these faults is often controlled by pore pressure, which modulates the normal stress on fault, and that can lead to either stable sliding behavior, or if it's low pore pressure conditions, we could end up getting larger, more stick slip events. So what I've been doing here is using laboratory measurements on representative core samples. So these are drilling core samples from places where we have sediments going into the subduction margin, so representative material that's ultimately going to go down and be subducted beneath the accretionary margin, or the accretionary wedge. Ultimately, these tests can be used to inform models of seismic hazard assessment, but I'm not going to get into that too much here. So a little bit about subduction zone background. We're probably pretty familiar with this, but here we have continental crust being thrust over top of oceanic crust. And then in many cases, a thin film of sediment on top of the oceanic crust being underplayed, subducted and underplated beneath the continental crust. So here in the upper portions of the subduction zone, we tend to have sort of stable sliding behavior. It's low stress conditions, so we get stable sliding, we get low frequency events, and we get slow slip. So we kind of think of this as sort of a quasi-stable regime. Down sort of once we get between 20 and 10 and 30 kilometers depth, we get more sort of seismic events, and this is where we get those great tsunamigenic earthquakes, and the seismic cycle that we're familiar with. Down dip of that below 30 kilometers, again, we have sort of more quasi-stable behavior as you get down into sort of the upper portions of the mantle. There are events that do happen, 100 to 500 kilometers depth. That's a different mechanism that I'll be talking about here, but it's just interesting to note that we have this sort of spectrum of behavior. The main portion that I'll be focused on here is this sort of zone in the upper portions of the accretionary prism, where we generally in seismic surveys, we observe these areas as having sort of low VP, high reflectivity responses in the seismic. And that correlates typically with undercompaction and high pore pressure. So looking at mechanical dewatering there, controlling the slow behavior. So my sort of target area here is the Eastern Aleutians. This is Alaska. We've got the Pacific plate subducting beneath the North American plate. The site that I'm focused on here is this drill site from Expedition 341 in 2011, where they cored at site 1417. That's the red point, sort of distal part of the surveyor fan over here. The surveyor fan basically is a turgeonous fan that sits over top of a lot of sort of older pelagic sediments. And so a lot of the work that I'm doing is correlating, measuring the properties in those pelagic layers, because that's a little bit more representative of the material that's going down in subduction zones around the world. Now, the Eastern Aleutians, again, like I've been saying, hosts a spectrum of slip behavior. We have a number of patches where we've had great earthquakes, obviously the 1964 rupture event with the 9.2. There's also what's termed the Samiti segment, which ruptured in 1938 in magnitude 8. And then there's this interesting location where we have a gap in sort of great earthquake seismicity, which is termed the Shumagen Gap. This zone hasn't had anything greater than a magnitude 6 over the last, I guess, 100 years. And so it's an interesting sort of comparison between the regions to the east of it and also to the west. There have been a number of seismic surveys that have crossed these margins. So the Aleut seismic lines, which I'm showing here, these profiles moving from 3, 4, and 5 westward. These are some of the data that I'll be used to compare it with my laboratory experiments. So a little bit about the geologic context at site U1417. The seismic profile on the left shows distinct differences in the sedimentation and the sediment characteristics between these seismic sequences. So units 3 overlying units 2, which overlies unit 1. So unit 1 here is basically everything from this yellow line, this yellow horizon, down to basement. Unit 1 here represents the sediment that ultimately will be underthrust in this portion of Alaska. And it's characterized by sort of late Miocene to early Pliocene clays and pelagic sediments. The important part here is that a lot of these sediments are pre-glaciation, so they were deposited when there was very low sedimentation rates. Units 2 and 3 here are sort of soon glacial and represent much higher sedimentation rates. Now, some of these ultimately may be subducted because of how far the site is from the margin, but primarily I'm focusing on everything, the sequence in unit 1. The key takeaway here is that this section is dominated by mostly pervasive mudstones and pelagic biosiliceous oozes. This is typical for a lot of sort of basinal sediments that have not been glacially deposited and are going to be entering these suction margins. So this could be compared to something like the Central Aleutians, where they've had very low sedimentation rates and it's not much sediment being deposited from continental margins. So a little bit about the workflow for this project. I start with sort of consolidation tests on cores. This produces laboratory outputs of VP, porosity, permeability, and compressibility of the sediments as a function of stress. And then comparing those with input sediment thicknesses from field measurements taken from seismic surveys. I put these into analytical constant rate of loading model, which I'll talk about in a little bit. And this outputs predicted VP, because VP is sort of the key parameter that ties together both laboratory measurements and also field scale observations. And then ultimately compare these with the PSDM measurements to then see if we can say something about the overpressure and the how sediments are dewatering it at sort of a margin scale. Okay, so talking a little bit about these experiments using laboratory derived compression behavior. These samples were deformed under constant rate of strain conditions in a uniaxial testing apparatus. The way this works is that you take a core sediment, you put it into a ring that's it's laterally confined, and you apply a vertical load to it, so vertical stress. This is done under constant rate of strain conditions, and we measure things like the pore fluid pressure within the sample. We measure VP throughout the tests, and we can compute permeability, compressibility, and what is called coefficient of consolidation, but you can think of it as a hydraulic diffusivity, and I'll talk about that in a little bit. The schematic here in the middle basically shows that there's a core sample that goes into the ring, and once we load it, we can control all of the pressure, the rate, and the stress that's being applied. The typical form of one of these tests in terms of porosity space, so you can think of this as the volumetric strain almost, is this plot here on the right-hand side and at the bottom. As you load the sample, you will elastically, because these are sediments, you'll recompress the sediments to their previous in situ stress condition. This is typically along an elastic recompression path and is recoverable. So if you were to then unload the sample and reload it, it would follow that same path back to that stress. Once you pass that sort of in situ stress, then you get into permanent plastic deformation. And so that's the sort of sharp slope down past the break that once you get past that elastic recompression phase. And this is what happens to all the sediments when you reload them. And so this allows us to get things like the behavior of the sediment as it's straining throughout a uniaxial stress condition. So a little bit of background on sediment consolidation. Most sediments behave in sort of this form where you have porosity decreasing with increasing depth or increasing stress. You can think of stress and increasing depth as one and the same, given certain pore pressure conditions. Now, this plot that I'm showing on the left is porosity for various locations, different sediments from different margins. These are input sediments to the Eastern Aleutians. These are also input sediments to other margins and also wedge sediments. So in general, we see this nonlinear behavior or nonlinear decrease in porosity with increasing stress. A lot of the times we typically we like to represent porosity change as a change in void ratio space. Void ratio is just the ratio of the volume of the voids to the volume of the solids. So it tends to be linear as a function of the logarithm of stress. And so it's a little bit easier to represent mathematically. Now, one interesting thing here is that the composition of the sediment does matter in terms of how sediment compresses as you load it. And so if you think of something that has a lot of clay in it, so a high percentage of clay, typically will have a larger slope in this void ratio effective stress space. And so that just means that for a given increase in stress, the sediment with more clay will strain more when compared to something that is more sand rich or quartz rich. Essentially what this means is that sediments with more clay will ultimately bear more load. With more clay the fluids within sediments with more clay will ultimately bear more load than the water within sand rich sediments. So ultimately what this means is that you'll generate more pore pressure when you load a sample that is more clay rich versus a sample that's more sand rich. So I've been measuring samples in the lab. So these are samples taken from, you know, the borehole at U1417, below 300 in the pelagic layers here, which are, you know, clay rich, but also have a good portion of silica, biogenic silica. And so this is a plot of void ratio as a function of stress, logarithm of stress, and the lab derived void ratios that I've measured here are shown with that little red arrow. These are also in comparison with porosities or void ratios measured on the ship. So these are the red point or the gray points here with the error bars, along with drilling data. So logging while drilling also reports on porosity. Field-based measurements taken from the elute lines, which again are measuring VP, but once converted to porosity, show this log linear behavior with void ratio. Now, part of what I've done here is refit a previous compression trend that was published in 2018 based on my new laboratory measurements. Ultimately, the takeaway from this figure is that the slopes between the compression trend that was published and my compression trend are the same, which is what we would expect them to be. The only refinement here is there's a little bit of a DC offset in void ratio. Okay, so shifting gears to laboratory measurements of VP, because ultimately VP is what we're using to compare it with seismic surveys. The VP measurements were done here campaign style during the CRS tests. This is again the elastic the compression path for sediment that was loaded uniaxially. And the red arrows here show the locations of VP measurements throughout the consolidation of this particular experiment. On the right-hand side, I'm showing a stacked version of each waveform, just showing the progression of the P wave arrival as you increase stress. So we start here at low stress at about 500 kPa and work our way up to about 36 MPa. And the P wave arrival correspondingly moves to earlier and earlier time, showing an increase in VP. So we can take those measurements of VP and fit them to empirical relationships that were developed for sediments at subduction margins. So one of these was published by Erickson Gerard in 1998 and has been used in a number of contexts for sediments entering subduction zones around the world. Here, what I've done is take our lab data, which are the red points, and I've fit this empirical relationship to them. And then I show an envelope of plus or minus 2 standard deviations around that envelope, or around that fit, which are the dashed red lines. I'm also showing a comparison with data collected from drill sites, DSDP drill sites, so at sites S183 and S186, which are located west of the Shumagon Gap. So these are a bit further away, but unfortunately, we don't have many drill sites that are near the location of interest. The blue points here are shipboard data. So this is measurements of VP and porosity from during samples taken during moisture and density logging, and also logging while drilling, so downhole measurements, the downhole logger in the drill hole. In general, this is the functional form of this is what we then use to transform from VP to porosity when you have a seismic line. So the last sort of set of mechanical data that we get from our uniaxial experiments are permeability and kind of coefficient of consolidation. Again, coefficient of consolidation, you can think of, if you know sort of what a diffusivity is, this is a hydraulic diffusivity. Here, the first measurement that we make is permeability. So the first plot is permeability as a function of effective stress. The colored lines here represent the uniaxial or tests in uniaxial stress conditions. So here where sigma 1 or the vertical stress is greater than sigma 2 and 3, which are the lateral stresses. And I've also compared these data with isostatic tests on some of the same samples under isostatic stress conditions. The reason for doing this is to see whether or not there is an effect of changing your stress condition, whether changing stress condition will affect your permeability, because if you take a sediment and subduct it, if you're suddenly not at a uniaxial stress condition, maybe the permeability will change, and that'll affect your interpretation later on. It turns out that it seems like permeability doesn't seem to care what stress condition you're at. These values are very similar, and so all it seems to really care about is what the porosity of the sample is, which makes sense because permeability is essentially a measure of how easy it is for fluid to move through the sediment. Now, the coefficient of consolidation or hydraulic diffusivity is the ratio of that permeability or the hydraulic conductivity to the compressibility. And so basically for something that is got low permeability and high compressibility, you'll have a really low hydraulic diffusivity. What that means is it's going to take a long time to basically dewater as you're compressing it. In terms of the data that we've collected for these tests, in general, these values, once we get past a certain stress, which is about 5 or 6 MPa, that value of diffusivity is roughly constant. As you can see, it doesn't vary much with increasing stress past about 5 MPa. And so in the models going forward that I'll talk about next, I use a constant value and vary that constant value of diffusivity in the models to predict what the pore pressure should be. Okay, so moving across to the PSDN lines of interest. Now, the Aleut lines were shot in 2011, I believe, and they cross the middle of the Shumagon Gap, middle and edge of the Shumagon Gap, and also the middle and edge of the Simiti segment and the middle of the Shumagon Gap. The PSDM lines were reprocessed recently by Donna Shillington, and she was able to extract for me the P wave velocity along the middle of the underthrusting layer. So if you look at the PSDM lines here, in line 3, you'll see these 2 red lines. Basically, this is the top of the decollement up to the point that we can't see it anymore, but then we project out a proto-decollement out beyond the trench. And then also the bottom line represents the base of the underthrusting sediment layer. So we have sediments that start out way outboard of the trench. They get into what will ultimately be part of that subduction channel. Then what we've done here is extract the P wave velocity along the middle of that subducting layer, because the conditions here we're going to be assuming are uniaxial. So that allows us to then compare laboratory measurements through a model to then compare with the field data. Key takeaway here is that you can immediately see that in line 3, which is the line furthest to the east, the initial thickness of sediment going into the subduction zone and ultimately being subducted is much thicker than lines 4 and 5. And so this is sort of a key thing to note going forward. Now, it is true that the U1417 is quite far the data that I'm collecting from my sediments is quite far from the locations at the alute lines. However, based on, correlating the sediments being pelagic sediments that were deposited in roughly the same age range as sediments entering the alute lines. So these are roughly late Miocene to Pliocene sediments deposited in low sedimentation rate environments, and they have similar P wave velocity VP profiles. So it looks like mechanically they're fairly similar, and they were deposited in similar times, and also they were both deposited under low sedimentation rate environments, so typical pelagic sediments. So using this as sort of a proxy for sediments entering that line. So the model that I'm using here is an analytical solution, one-dimensional solution, analytical solution to the consolidation equation. So it's essentially taking a piece of sediment, a package of sediment outboard of the subduction margin, taking it under a uniaxial stress path where we have a constant loading rate. Again, we're defining the plate rate here, so we have a constant rate at which these sediments are subducting. And then making a simplified assumption about the geometry of the wedge. So if what I'm doing here is taking a constant taper angle, a constant plate rate, and then predicting what the stress conditions are within that subducting sediment as you go from time of 0 to time n. Now, the main assumptions about this model are that the decollement is weak and that horizontal stresses are not transmitted below. And so I think this is a reasonable assumption based on studies of friction of sediments along decollement and also within material that shears at these margins. Basically what that means is that since stresses aren't transmitted horizontally below the decollement, what we see is that subducting sediment is under uniaxial stress conditions. And so this is why measurements in the laboratory of uniaxial deformation make sense in this context. In terms of how sediments drain in this model, it's the sediments are forced to drain vertically with no lateral drainage. So this box over here is basically showing us that the boundary condition is that there's no flow laterally, only vertically. So I'll go through these models a little bit slowly since there's a lot here. The first plot in the right hand, on the left-hand panel at the top is showing the direct output of this model, which is the degree of consolidation. Basically what this means is that at any point along the transect, you will have compression of the sediment, and that compression is being shown relative to a fully undrained or a fully drained case. So in this case, in this situation, a value of 1 here would be a fully drained sediment. So this is something that dewaters as quickly as you're loading it. So you're not developing any pore pressure. The value of 0 here is a completely undrained sediment. So this would be basically you'd be loading it, and the fluid pressure developed in the sediment would be equal to the applied overburden at each location throughout the transect. The other 4 lines here are model outputs for different values of that hydraulic diffusivity that I've been talking about. So this is that C sub V term. These values here are ranging the span of the values that I measured in the lab. So 1 × 10⁻⁷ for the highest diffusivity, down to 1 × 10⁻⁹ for the lowest. And so that's the highest here. Highest diffusivities here are represented by the lightest curve, and then the darkest curve that's not 0 is the lowest diffusivity. The 2 curves in the middle are bounding plus or minus 10% of the mean of my laboratory data. So that's basically what we think is the best fit for this model. So those 2 thick middle gray curves. the curve, the plot in the middle, so P star, this is the pressure in the pore fluid pressure less the hydrostatic. And so this is very similar in terms of its interpretation to the degree of consolidation, except here a value of 0 means that the pressure within the sediment, or the sediment, is acting completely drained, whereas because you're subtracting off your hydrostatic, so value of 0 here means it's completely drained, whereas the highest curve, or the darkest curve, means that your sediment is completely undrained, and that is a representative of the lithostatic load. Now, finally, what we can do with this, because I've developed those, the compression trend, which is the porosity or stress porosity transform from the laboratory data, and then I have that porosity P wave velocity transform again from laboratory data. I can calculate what the pressures within the underthrusting layer is, to then calculate what the expected P velocity should be. So again, here the P velocity is showing a range between a completely undrained case, which is the flat line, the flat black line, and then a fully drained case, which is the dashed line at the top. So again, if you have something that is completely drained, you expect it to be faster because you're more consolidated. The red line here is the P velocity extracted from the underthrusting layer at line 3 with the associated error in that PSDM. And the key thing to note here is that the P wave velocity actually seems to be predicted fairly well by the curves that represent the diffusivities we measured in the lab. So, which is pretty interesting. The key thing here is that the initial sediment thickness for line 3 is about 660 meters. And I'll be talking a little bit more about the importance of initial thickness in subducting sediment layer as we go forward to sort of implications. Moving on to line 4, so here we're moving a little bit further west. Here, the initial sediment layer is thinning, so we go from about 650 meters to 450 meters thick. And here, the key thing to note, looking at the model curves and what we would expect to see, is that we would expect more drainage because the sediment layer is thin. So the path length for water to get out is quicker, or it's shorter. And that's what we tend to see, is that with the thinner sediment layer, we get a higher measured velocity. And so in that, the red curve here is sort of following the predictions that we make for sort of faster drainage and more hydrostatic pore pressure conditions. And again, moving a little bit further west to the middle of the Shumiden Gap, this is where we have line 5. The initial sediment thickness here is about 250 meters. And again, as the sediment thins, what we're seeing is that progressively we drain the sediment more, which means that the P wave velocity is faster than the hydraulic diffusivities would suggest. So comparing, one of the things we can do is sort of estimate what the pore fluid pressure ratio is within that underthrusting sediment layer. So these are reference curves based on the laboratory data that I've collected, comparing the underthrusting extracted underthrusting P wave velocity to a reference expected P wave velocity given a pore pressure condition. So here, the pore pressure ratio, which is lambda star, is just the ratio of the pore fluid pressure less the hydrostatic over or to the vertical stress less the hydrostatic. So we're removing hydrostatic from this and comparing the expected, what we predict P wave velocity to be for various pore pressure ratios to what they are measured. And so what we see is that in line 3, we typically have values here that are much higher. So this is so a higher pore fluid pressure ratio represents something that's more undrained. And then something, lambda star of 0 would be something that is completely drained and hydrostatic. So basically once you get down to 4 or 5 kilometers in line 3, what you see is that the pore fluid pressure ratio, or the predictions, match what you would get for a pore fluid pressure ratio of 0.6. And so this just means that this is basically showing that we are draining better in the thinner layers that are subducting. The plot on the right-hand side is showing the deviation in VP from what we would, from a hydrostatic condition. So basically how much, you can think of this as a residual VP in a seismic survey sense too. So what this is showing is that for a lambda star of 0.6, which is what we get in line 3 at about 4 kilometers depth, we have a deviation in VP from hydrostatic of about 25%, which is pretty interesting. It's quite significant. Okay, so thinking about this in the context of other subduction zones around the world, one of the things that's interesting is that we can take measurements of the residual VP at different margins and then compare them to the loading rates at those margins, because the thickness of the sediment is really what's controlling the rate at which sediments dewater, because it seems like sediments tend to have permeabilities and diffusivities that are within an order of magnitude of each other. And so what else changes around the world? Well, subduction rates change because you have different plate rates and you have different taper angles. You also have different input thicknesses. And so what I'm showing here is a comparison between the different subduction zones where we have VP measured and estimated based on what we'd expect it to be. So this is sort of a residual VP on the y-axis, and then your loading rate on the x-axis. So this is a sort of a functional form of what we would expect VP to be at different subduction zones at a certain depth. Basically what this is saying is that if you have an input sediment thickness that is quite high, after you get past a certain point, you wouldn't expect the residual VP to change a ton. Whereas initially, if you have thinner input sediments, thinner input thicknesses of sediments, so down here at this part of the plot, you have sediments that are relatively thin, that are being loaded quickly. And so basically what this is saying is that there's 2 ways to generate that overpressure, which is either your thick sediments or your initial loading rates, your fast loading rates. So in conclusion, this has basically been, the idea behind this has been to measure the mechanical and hydraulic properties of sediments as they're entering modern subduction zones. Here I'm showing the Eastern Aleutians, using the model and also the laboratory data to show that that sediments tend to be overpressured when you tend to have thicker input sediments, but also with faster loading rates. And then in places where sediments are relatively thin, these tend to consolidate quickly, and so you don't generate nearly as much pore pressure beneath the decollement in the upper portions of the subduction zone. Now, the implications here basically lead to imply that, especially in areas where we have very thick packages of sediments going in, a lot of the times we can get very large earthquakes, which is what is correlated here with the Samiti segment. Here we have a thick package of sediment entering that's struggling to dewater, so you're transporting a lot more water down dip. And in regions where you have thin sediments going in, if they're consolidating, dewatering quickly, then maybe the underlying topography of the oceanic crust could have more of an impact on slip and frictional properties of the decollement. So yeah, with that, I can take some questions.
Sweet. Eric, any questions? Zoom, any questions? There's not many people today, so anyone with questions, please just speak up.
Hi, Peter.
Hey,
This is
Alejandro.
Alejandro. Yeah, so I have a question about the model.
Mhm.
So one, like, I was confused at the beginning because you said the sediments in the model are uniaxially loaded, but these are the under thrusting sediments, right? The sediments that are in the wedge, those are not uniaxial, right?
Correct. In the wedge, they won't be.
Yeah, okay. So I have a question for the initial condition
Mhm.
once those sediments enter and are being subducted. So the initial condition they are normally consolidated, so pore pressure equal to hydrostatic.
Correct.
Yeah.
Yep. Here, I'll go
So
back to that.
I guess my question is what are the sedimentation rates in the basin? Are those low enough to say they are hydrostatically at T0?
Yeah, so the sedimentation rates, especially out incoming to the elute lines, what is certainly very low when those sediments were deposited, on the order of, I think, between 30 to 50 meters per million years, something along those lines. It's low.
Well, and I guess you can with
But
this
yes, I can.
sedimentation rate, you can check if this would be overpressure or not, right? Like with
Yes.
with experiments, right?
Right, and so also the thickness of the sediment based on the sedimentation rate, I could calculate what the whether or not it would be overpressure or whether it should be overpressure to start with.
Yeah, exactly.
Again, the assumption here is that they're not. That's also based on observations of P wave velocity from seismic lines compared with the laboratory data. And so if that's similar enough that we expect it to be, we don't expect the sediments to be overpressured, but that is something to check for sure.
Okay. So if no one else has more questions, I do have more questions.
Go ahead.
So the last plot, it was a bit confusing because of the slide 23, yeah. So
Yeah.
the horizontal axis, that's like roughly a measure of how fast the sediments are being subducted, right? Like in your case, it was
Yes.
the 55 millimeters per year.
Correct. So the VP, right? Yeah, I guess I didn't explain this that clearly. VP here is the plate rate. The tangent alpha plus beta is the taper angle, and so that is essentially the loading rate for a particular wedge geometry. And then the h squared, because hydraulic diffusivity is often calculated as a function of, well, it's calculated as a function of permeability and compressibility, but the rate at which pore pressure is developing scales with your thickness, the square of the thickness. And so that's why the initial thickness here is squared and multiplied by that plate rate.
Okay, so and then the color bar then represents the sedimentation rate at the basin, I guess, right?
The color bar just represents the initial thickness of the sediment that's ultimately going to be subducted. So that's just showing that places like Cascadia, you can see that it's sort of way out there at about. So Cascadia is out on the right-hand side of the plot compared to thinner input sediments on the left. That color bar just again represents that initial input.
Okay, I understand. Yeah. Which again, it represents sedimentation rates plus how old are the sediments, I guess, right?
Yes, you could
Sort
think of it that way.
Yeah, something like
Yeah.
that. Okay.
Mm-hmm.
I have some questions.
Go ahead.
One of them is like a conceptual question. So you have some sediment package, let's say, at your drill site. And then it eventually goes into the subduction zone and starts plunging beneath the continent, right? And its orientation changes as that happens, right? Because the place starts to dip.
Yeah, so is your question, what is the?
My question is just like conceptually, you can imagine where you're applying some uniaxial stress in the straight up and down. But then as you get deeper, the angle of that stress is changing. And am I thinking about this wrong, or is that a real effect? And how does that fit into?
You're thinking about that correctly, but I'm making a couple of assumptions here. The first is that it's slippery enough so low enough friction that we're not transmitting any stresses horizontally because of that. Because if you think about having something that is frictionally strong as you're sliding it underneath something, you're also transmitting a horizontal stress to that. So I'm assuming that that's not happening in the model for simplicity's sake. The second thing is that, yes, that's true that your stresses will be oriented slightly. Your vertical stress might not be, or your total vertical stress will not be the same as what's being applied normal to the fault surface. So that is true. Again, that's a really small angle. It is measurable, but here I'm assuming that that's not a big factor in terms of the overall stress applied. So that is a nuance that could be added for sure, but is that?
Yeah. I have an unrelated question, if there's not any more. Why, in your understanding, should these thicker sediments essentially, I guess, dewater less efficiently? Like, if you assume it's homogeneous or whatever, right? It's like, what about sediment thickness is creating this effect?
So you can imagine it as having, so permeability is basically how easy it is for water to get out, right? That's just a measure of how easy it is for water to move through a package. As you increase your thickness, that path length that it takes water at any point within the sediment to then get up and leave is going to be proportionally longer based on how thick the sediment is and how quickly you're loading it. And so that's why this h squared term is kind of important, is because it's for each unit of height that you add, the time it takes, or the rate at which you increase pressure scales with the square of that distance. And so again, it's just purely how quickly can you get water out. And because these are clay-rich sediments, they are relatively compressible. And so the fluid also bears a lot of that added load. So that's, as you increase, there's a lot of factors that pile up to allow the sediment to build up more pressure quickly. And so that's why you can start with, if you double your thickness, you can go from something that dewaters quickly to something that doesn't. So.
Any other questions? Zoom? All right, well, if there are no other questions, thank Peter one more time for giving his talk today, and we'll see you guys next week.
Thank you.